Good morning. I'm glad you're here and that you're ready to learn. Today we're in section 614, and this section bears the title, How Can I Use Variables to Solve Problems? The big idea here is, yes, we'll be using variables, but a really important thing to do when you use variables is to write let statements so that we know exactly what that particular variable is tracking. We'll also look at some problems that involve distance, rate, and time. Those three values, distance, rate, time, they all have units associated with them. And just thinking about dimensional analysis, we will see that there's a clear relationship between those, amongst those three variables, looking at their units. So let me read. Today you will learn to translate written information into algebraic symbols and solve the equations that represent the written relationships. This is not a simple task. This is something you've started already, and something that we're going to continue to do. You're going to continue to do. So our first activity is there are these four equations and four written descriptions of those equations. And what I'm asking you to do in Desmos is to take the written descriptions and match them with the particular equations. So each one of them would be matched somehow. And once you decide, like we're not going to join words with words, right? This would not be a match that we would want, but I could take this equation and match it with this if I think that these words can be modeled by this equation. So that's the first thing that I want you to do, is read these carefully. I do say that if you're working with others in your group, remotely or in the classroom, make sure that you're in agreement before you click the next button and you move on. In question 32 it says, mathematical sentences like those in the left column of problem 6-31 are easier to understand when everyone knows what the variables represent. A statement that describes the variable, what the variable represents, is called a let statement. For example, and this is a giveaway, for mathematical sentence above, right, which is matched with translation 2, we could say let Z equal Zola's rate of pay in dollars per hour. So this is a complete let statement, and it contains the following items: the word let, the variable that you're letting equal something, the equals, so I mean we're setting the Z equal to this thing, let Z equal, and then here's Zola's rate of pay. Not just let Z be Zola, but well, Z is not Zola. Z is not the hours that Zola worked. Z is not the money that Zola earned. Very specifically, Z is the rate of pay, Zola's rate of pay, and then you can see it has units, right? Dollars per hour, not pounds per minute or some other current pesos per day or whatever it is. It's dollars per hour. So it contains all of those components. And I'm going to ask you here to write let statements on the next slide in Desmos, to write let statements for each of those. The next problem says one equation or two. One of the things that should have happened in a normal academic year in 8th grade is you should have gotten some practice at solving equation problems like this using a single variable, and a single equation. We're going to look at setting these things up with multiple equations and multiple variables, just because it gives us more flexibility and opens up the possibility of problems that can be solved. So this is the next problem that you're going to solve in Desmos, or record your result in Desmos. So the problem says Elsa took all of her cans and bottles from home to the recycling center. The number of cans was one more than 4 times the number of bottles. So if you look at this, to me, the fact that they're giving me what cans is in terms of bottles tells me that I probably would want to write my let statement being let B equal the number of bottles. So if I said that let B be the number of bottles, then I could represent cans. Cans equals cans is cans was one more than 4 times the number of bottles. So 4B plus 1 is the number of cans. Cans is one more than, that's the plus 1, 4 times the number of bottles. So that's a thing to think about there. How do I know which of my variables should I use for my let statement? Well, if you see that a lot of the variables are being, or quantities are being defined in terms of one thing, make this the let statement and then use this variable to define how many cans she had. It says she earned 12 cents for each bottle and 10 cents for each can and ended up earning $2.18 in all. How many cans and bottles did she recycle? Okay, so we have two people here. We have Solomon and we have Marcus. Solomon wants to solve the problem using just one variable. Define a variable using a let statement, then write an equation that Solomon could use to solve the problem. So for this problem, I'm looking for a let statement, and then I'm looking for an equation that he could use to solve the problem. So if I was to click into here, I could clearly type just normal text, let t equals, and then something, right? Remember that in these boxes, I can do both math and I can do just plain text. And I wanted to change this so that you see it's a little bit clearer. So now you can see if you want to jump and type math anywhere in here, you could just click this. But I could, this is not math, so I could just set let B equal the number of bottles. B-O-T-T-L-E-S. So B is the number of bottles. It's a count, right? It's not bottles per box. It's just how many. So it's just the count of them. And then we need to write an equation that we could use to solve this. Well, we know that we have B bottles, right? And every single one of those bottles earns us, let's see, she earns 10 cents for each, or 12 cents for each bottle. So I can say she earns 0.212 cents for each of the bottles. And then plus she earns some money for the cans, and it's only 10 cents for the cans. So again, how do I describe the number of cans? Remember, the number of cans was 4 times the number of bottles plus one more. So what I just typed there represents how many cans I had, because the number of cans was, it says right here, it says the number of cans was one more than 4 times the number of bottles. So you can see this is the number of bottles, B, right? Why do I know that? Because of my let statement. And then plus the number of cans I have, and then each of the cans is going to be multiplied by 0.10 cents. And together, those two quantities equal $2.18. Now I noticed that I didn't type math, I didn't use the math formatting there, and it actually wasn't necessary for this because there's no exponents, there's no square roots, there's no fractions. But I could, just to change the format a little bit, select it all and hit it. So now we can see that a little bit better. Let me, a little bit better. So we've got our let statement, and then we have an equation that describes, I have money from the bottles and I have money from the cans, and that equals $2.18. Moving on now with the same exact problem, right? Marcus wants to solve the problem using two variables. Define your variables using a let statement, actually two let statements, and then write the two equations that Marcus could use to solve the problem. You do not need to solve the equations. So we're dealing with two different things, right? Bottles and cans. So I could say let B equal the number of bottles and let C equal the number of cans. Okay, so if those are my two equations, I mean those are my two variables, I need to write not just one but two equations to solve that. So it is true that the number of cans, and let me type this with math, type the math formatting. The number of cans is equal to, they said 4 times the number of bottles plus one more. What it really said was one more than something, one more than 4 times the number of bottles. The other thing that's true is if I take the number of cans I have, and let's see, let's do this. I think each can was worth 10 cents. So if I go 0.10 C plus 0.12, each bottle was worth 12 cents B. So you can see what I'm saying. 10 cents times each can. So the number of all the cans, if I have 10 cans, 10 times 10 cents is $1, right? So the number of cans times 10 plus the number of bottles times 12, and that equals $2.18. So now I've got this situation where I have two different equations, right? And I know what each of the variables represent here, but this should apparently be the same problem. Now, if you were able to solve the problem up above, you could plug that solution in from above and see, is it really the same thing? So the question below is, do Solomon's equations and Marcus's equation, actually that's singular, there should only be, he only had one, represent the same problem? So I want you to explain that here and then share that response with the class. So the final problem you'll do in Desmos, there's one more thing we'll discuss in our notes before we quit the session, but the final thing you'll do in Desmos is this problem. It's on screen number 5, and it says, after reading about earning money by recycling, Solomon and Marcus are excited to do some recycling themselves. Solomon has some electronics his parents said he could recycle. Marcus has permission to recycle some small household appliances. They looked online and discovered that the local recycling center offers 60 cents per pound for the appliances and $1.50 per pound for the electronics. But there is a $27 hazardous waste fee that has to be paid to recycle the electronics. So you're getting more per pound of electronics, but you've got to overcome this $27 hazardous fee, because it says, but there is a $27 hazardous waste fee. So that's something that we're going to have to be paying. That has to be paid to recycle electronics, no matter how much you recycle. So if you just recycled 1 pound of electronics, that's going to cost you money. So our problem here, it says, write one equation that represents how much money Solomon would earn from recycling electronics. Write another equation that represents how much that represents what Marcus earns from recycling appliances. So you can see I've got spots for 2 equations here: equation for Solomon, equation for Marcus. And this will allow me to bring up the math type. Yeah, I can type in the math. And then the final question after we have each of these, the last question is, how many pounds would they have to each recycle so that they earn the same amount of money? So I don't want to know, this equation is going to describe how much Solomon earns. This is going to describe how much Marcus earns. I want to know the pound number, right? The pound that has to be, so that each of these give me the same output. They give me the same dollar value. So that's I'm being much less helpful here. I want you to think through and work through this one, and definitely you can consult with other students. It doesn't have to be completely alone, but I'm not going to just tell you this answer. Okay, so we have 2 more problems that we're going to look at together, 35 and 36. As we're working through these, please feel free to pause at any time. You can look at 35 in the textbook and work on it independently, and then just come back in and check and see if you agree. Or you can work with it with other classmates and come back in and check and see if you agree with what I'm writing and what I'm saying here. Summertime camping. Morgan and her family are camping on their summer vacation. Morgan decided to take a bike ride before it got too hot. She left the campsite and rode her bike at a speed of 16 miles per hour for 1.5 hours. How far did she ride? So the thing that's interesting about A is if you just look at the units, right? She's riding 16 miles per 1 hour, and she's doing so for 1.5 hours. So if I just look at that just from a dimensional point of view, right? If I look at my units here, I've got miles per hour times hours. Well, if I multiply miles per hour times hours, notice that when I do that multiplication problem, those units cancel, right? So miles per hour times hours ends up giving me just miles. So yes, there's an answer here, but the unit is miles. So it's interesting. The question is asking how far did she ride? Well, I can see if I multiply the miles per hour I'm given times the hours I'm given, it's going to give me an answer in miles, and it's just some number that we'll fill in right there. But I want to point this out, right? This relationship is showing me that if I take my rate, my miles per hour, and I multiply it times a time, right, I get, I get a distance. So this, right, this insight, rate times time is distance, or distance equals rate times time. I could see that just by looking at the dimensions here. And if I don't have to know that at all I have to know that, yeah, it's absolutely true that if you multiply miles per hour times hours, you really do get miles. So if your rate is in miles per hour, and your distance or your time is recorded in hours, the answer you'll get for distance will be in miles. So that's A. B. Morgan's dad went to get groceries at the camp store at the bottom of the mountain. He drove 20 miles. He drove 20 miles. He drove 20 miles per hour for 0.4 hours. Oh, I'm seeing the exact same thing again, right? He's driving 20 miles per hour, and he's doing so for just 4/10 of an hour. And again, when we multiply these, just looking at it from a dimensional analysis point of view, miles per hour times hours is going to give me miles. So my answer here is going to be some number of miles. And then finally, when Morgan's dad returned from the store, he went for a jog. He jogged for 1 hour and 15 minutes at a pace of 4.8 miles per hour. So he jogged for 1 hour and 15 minutes. Now it's an interesting unit, right? Because I can't write 1 hour and 15 minutes here, right? I need this to be just one thing. I can have hours or I can have minutes, but I can't have both. Now, it's interesting that they do tell me that he was jogging at a speed of 4.8 miles per hour. So I know that I want his speed or his time jogging to be expressed in hours, right? If his time jogging was expressed in hours, when I put it there, those hours will cancel with these hours, and I'll be able to figure out the distance. So this is a side problem. How do I express 1 hour and 15 minutes as a decimal? Well, we're like, well, that's easy, Roberts, because 15 minutes is 1/4 of an hour. So we can just go, that's 1.25 hours. And that's true. That's a great observation. It's very clever. But what if I told you it was 6 minutes? What if I told you it was 3.4 minutes, right? What's the mechanics of turning a certain number of minutes into hours? So we can come back and think about this from a dimensional analysis point of view. If I have 15 minutes and I want to express that in hours, the question, I want my units at the end to be hours. The question is, what do I multiply it by? Well, it's going to be a giant 1. And I think about this, I want the minutes to go away, so I immediately know that minutes are going to live in my denominator. And I want to be left with hours when I'm done. So what I have to do now is put numbers here to really make this a giant 1, because 1 hour is not the same thing as 1 minute, but 1 hour is the same as 60 minutes, right? So I can see now the mechanics here. If I want to convert minutes into hours, I just multiply by 1/60th, right? And then my minutes over minutes cancel, and I'm left with exactly hours. So and yes, if I take a look at 15 over 60, that is the same thing as what is that? It's 30. It is 1/4, right? It is 0.25. It is 0.25. It is what we said it would be. It's 1.25 hours. All right, so when we put down that the dad drove, the time he jogged was 1.25 hours, right? 1 hour and 15 minutes. You can see that our hours over hours will cancel and we're going to be left with miles. So this relationship is something that we should be aware of. Distance is equal to rate times time. The distance you travel is equal to the rate you travel times the time you travel. Now, this equation can be manipulated in a whole host of different ways, right? You can do things with it. For example, you can say, I could divide both sides by t, and I could say then rate would equal, or actually if I'm dividing by t, I'll do this. I'll say distance divided by time is rate. So this equation is obtained by taking the first equation and dividing both sides by t. I could also divide both sides by I could divide both sides by r. I could take this equation. I could take this equation and divide both sides by r, and I would get distance divided by your rate is apparently equal to time. So these are all useful incarnations of this one fundamental idea that distance is equal to rate times time. Okay, so final thing then is question 36. It says, each of the parts in problem 35 involve 3 units of measure. You were given 2 and then calculated the third. What 3 units of measure were common to all parts of the problem? You can look at what we just said. And then write a single equation that models this relationship. Again, we just spelled that out. So the last thing that I need you to do and add to your notes is question 36 is parts C, D, and E. I am going to be online during office hours today. I'm prepared to discuss these. I want you to see if you get those right, if you understand them. Also, my posted solutions are available too, so you can click and look at those. But make sure you understand how to do C, D, and then respond to part C, D, and then respond to part E. All right, that's it. 22 minutes, 30 seconds. Hope you have a great day. I look forward to seeing you both in class and online this week. Talk to you later.